Okay, so let's look at this problem and see what we've got. Again, it wants to determine the horizontal and vertical reactions at A and C. What does A look like to you?
Pin.
That's a pin. And it looks like C is also a pin. So if you try to draw a free body diagram for the whole structure, you're going to have two unknowns here and two unknowns here. That's 4 and only 3 equations. You're not going to be able to get everything. You might get some of it. You might get partial answers, but you won't be able to get the whole. So is there some way we can solve this problem? Yeah, I think I even mentioned here, it said you can view, oddly enough, BC, this weird angle, is a two-force member. Right? It's pinned at both ends. There's no load applied. So it's back to the example I had on the board here of kind of a crazy snake. So I know if I draw a line between B and C, I know that the reaction on B is going to be in that direction. So really all I need is a free body diagram of AB. So I'll do that first. So my free body diagram of AB. So I'll draw that. That's 5 meters tall. So at A, again we'll assume AY, AX. And I'm going to come over here and draw some force that I'll call B again. Now how can I know, how do I know the direction here? Well, it looks like it is, the slope here would be 4 across and 5 up. So that will be a weird slope, but that will tell me the direction I need. 4 to 5, right? I think I'll draw that later up here so we can see it a little more clearly. And then the distributed force on the left-hand side is rectangular. So again, that's easy. The equivalent force would just be the area of the curve, which is the base times the height. The base is 5 meters. The height is 350 Newton per meter. What is that? That's 1750 or 1850? 1750? $17.50. So that's 1.75 kilonewtons, right? I'll do it that way. 1.75 kilonewtons. It happens right in the middle, so that would be 2.5 meters from the bottom or the top. There's my free body diagram. So it's kind of interesting, the thought process that goes into turning that into something that... So that's why it's important to me. I mean, there's a lot in distilling the general problem down to something that can be handled quickly with the mathematics. So that's why I give you a lot of credit for that. I avoid sine and cosine whenever possible because I just don't like them. I didn't like them when I saw them the first time. I don't like them now. But it's not a personal thing. I just don't like them. So what's the hypotenuse here? So it's 16 plus 25. What's 16 plus 25? Anybody know that?
6.4.
What is it?
6.4.
No, what's 16 plus 25? 40? Is it exact? 41? So this would be the square root of 41, right? The hypotenuse? Right? Because the hypotenuse is this squared plus this squared, take the square root of that, right? So 16 plus 25 is 41, take the square root of 41, right? Yep. See, I hadn't used my calculator yet, except I have to do 16 plus 25. I should have got out my toothpicks. I could have done it with toothpicks. So now, when I want the x component of this, I just take 4 divided by the square root of 41. It's done. That's the cosine of that angle. And I want the vertical component, I just take 5 divided by the square root of 21, and that's it. I don't have to find sine, or sin and cos, as people used to say. Okay? So now what do we do? Let's apply our equations of equilibrium. Should I sum forces in the x direction first? No. Well, you can, but you'll get one equation in 2 unknowns. How about y? Same. So somebody's asking, well, let's just solve some of the forces in the X, some of the forces in Y simultaneously. You are welcome to do that. It's not terribly hard, but you'll probably make a mistake, especially in the heat of the battle. So I suggest that you, some moments about the pin. We may do this just a few times this semester. Some moments, assuming right-hand rule, about a pin at A, make sure it's in equilibrium. So let's do that. So I have some moments about A, what do I have to worry about? Do I have to worry about the X component the Y component of B? No, because it's going to pass through A. But I do have to worry about the X component. And what I'll do is I'll draw it in so you can just kind of see the direction. It's kind of going that way. So is that going to create positive or negative moment about A? Positive. And what is that force? That X component. It'd be 4 over the square root of 41B. That's the X component of B. You're saying, I don't like to do it that way. Well, how would you do it? You would probably take the arc tangent of 5 over 4 and get an angle. And then here you'd be taking the cosine of that angle. And you know what you get? You get that number right there. So it's just another way of doing it. Okay, so that's the force. What's the distance? 5 meters. What else creates a moment about A? Our 1.75 kilonewton force. Is it going to be positive or negative? Negative. So we're going to have minus force, 1.75 kilonewtons. And the distance from A to its centroid, well, I have that numbers right there. 2.5. So solve for B. What do you get? I have no idea. Anybody else get 1.4? I see one head shaking. Yep. All right. We got enough head shaking. 1.4 something?
Just 1.4.
And that will be kilonewtons. And it looks like it came out positive, so we have the right direction. And now we know B, we can plow ahead. So, I'm going to sum forces in the Y direction. Don't have to do this first. I could have summed forces in the X direction if I wanted to. But we'll sum forces in the Y direction. So I have AY acting up. That would be positive. Now what about the Y component of B? It's also pointing upward, right? So it's going to be positive. What is the Y component of B? Yeah, look at my triangle. It's 5. That's the vertical component. It's going to be 5 over square root of 41. And that's going to be B. I know B. I can plug it in there. I should be able to solve for AY. What do we get?
1.1.
Is it positive or negative?
Negative.
1.1, that'd be kilonewtons. So actually the reaction at A is holding the structure down. Does that make sense? Well, what do you think would happen if this is a big wind force on the side of your building? Is your building going to be driven into the ground? No, it's going to be lifted up. So you need your support to hold it down. A lot of people don't think about foundations of buildings. You think about them holding the building up. But do they ever have to grab the building and hold it down? Oh, all the time. All the time. Especially when the wind blows. That's right. This is the thing that your roof does not have. That's why your shingles go flying. They're not held down very well. Okay, so we're left with summing forces in the X direction. I'll assume right is positive. So there's our equilibrium statement. And what do we have? We have AX, which is to the right, so it'll be positive. I have my applied load to the right. It is also positive. And then I have my horizontal component of B, which we've already done before, which we know is to the left, so that's negative, and that will be 4 over the square root of 41b. And of course we know b, we can plug that in there. So what's ax? I have a feeling it's also going to be negative. I don't know why. Anybody get that one? No participants this time? No one playing at home? Bored already? Someone guess.
2.8.
57. What?
2.8.
2.8. Positive or negative?
Negative.
Anybody else get 2.8? No. I saw a no back there. No, not what did you get?
You said yes.
Oh, you said guess. Oh, that's a good, great guess, but it's wrong. What?
Negative 8.75.
8.75?
No, 0.875.
0.875. Is that right?
It will be negative. Negative 8.75.
0.875? Well, that was surprisingly more difficult than I thought. Okay. That kind of makes sense. This structure is being pushed to the right. Now, I know my big support here is helping balance that, but the reaction is a little to the left, so the reaction is still having to hold some of that horizontal force back. Okay.